Hi, this is Doris, and this summer I looked at bridging traditional and innovative solutions for the rocket equation using AI. My partner was Maya Bayret, and our mentor was Professor Argudo. At the start of our project, we used ChatGPT to study and better understand the rocket thrust equation. But in our conversations with ChatGPT, we actually discovered some inaccuracies in the explanation it was giving us. So in this snippet of our conversation, you can see that ChatGPT tells us to use F equals dp dt. However, this is not valid because the rocket thrust system is a variable mass system, and instead F equals ma has to be used for the accurate solution. After we became more familiar with the rocket thrust derivations, we moved on to modeling it using ChatGPT and Google Colabs. And what we did here was comparing the numerical solution and the analytical solution. The numerical solution was the Euler-Cramer method, which uses the initial velocity at the start of a time interval to calculate the velocity at the end of that time interval. And this gives a very, very close but not entirely accurate calculation for the velocity. And then the analytical solution would be the one based on a derived equation to calculate for the velocity at any given time. As you can see here with our three graphs and our animation, we created three separate models. The first was with the external force being gravity and only gravity. The second was the external force being only drag. And then the third was the external force being both gravity and drag. And because the external force with gravity and drag for that system, there's no known analytical solution. We tested the first two with gravity and with drag respectively. We tested those two separately, the numerical method, and then once we had those verified, we were able to alter them to include both gravity and drag and to model that without having an analytical solution. And we also used ChatGPT to create this animation with realistic variables. Next, we studied the physics-informed neural networks, also known as PIN. And what a neural network does is it predicts an output based on receiving an input, and it does so using a set of experimental data, which it will use to kind of fine-tune itself to match that. However, a big downside to this is that it fails to generalize away from the data. This is where the PIN comes in. PIN adds known differential equations as a loss function to improve the accuracy of neural networks and to make sure that that neural network solution is actually consistent with physical systems or in the physical world. There are 6 main steps to using PIN. The first is to define the problem. The second is setting up the environment. Third is building the network. 4 is embedding physics. 5 is training the system. And then 6 is validating and analyzing it. In our exploration of PINs, we found that SoftPlus was an effective neural network for our specific model. And as you can see in this picture here, as the training steps increased, the graph became more and more accurate. So in conclusion, we looked at the rocket thrust equation and how ChatGPT engagement has to be used through a critical lens. And we also modeled the rocket thrust equation with different external forces and explored how PIN can be used to also achieve solutions that are difficult to solve manually.